Hello and welcome, class. Welcome back to NUR 410, week 7. Everybody has been doing an excellent job. Continue to text me, call me, email with questions. I will try to respond within 24 hours. Text is probably most convenient for most of you guys. In this week's lecture, we're going to be looking at analysis and reporting of quantitative data. So a little introduction. If descriptive analysis answers the question, what is going on? The inferential analysis answers the question, are you sure? The word inferential means that the reader can infer something about a population's response to an intervention based on the responses of a carefully selected sample. Inference requires the calculation of numerical values to enhance confidence that the intervention resulted in the outcome and to rule out the possibility that something else did. In quantitative inferential analysis, that something else is error in all its forms: sampling error, measurement error, standard error, even random error. An inferential analysis allows the researcher to quantify its effect. When reading quantitative analysis, it is important to focus on both the probability of error and the certainty of the estimates. When quantitative analysis is used as evidence for nursing practice, the nurse should also consider the size of the effect and determine whether it attains both statistical and clinical significance. When creating quantitative analysis, the focus is on choosing the correct test and making appropriate decisions about its application. All of these factors are critical for ensuring that the relationship between intervention and outcome is one that is defined with certainty, so the results can be expected to be replicated in different settings among different people. Some general rules of quantitative analysis. Quantitative analysis is a highly systematic and organized process. Data for quantitative analysis are represented numerically, so the reliability of data collection, accuracy of data entry, and appropriateness of data analysis, data analytic processes are critical for drawing the correct conclusions. Because these types of analysis can be complex, a plan for analysis and reporting is determined when the methods and procedures are designed. A wide variety of statistical tests are available, each of which has specific requirements for data preparation and analysis. There are, however, some general guidelines for the way quantitative analysis are conducted. Select tests a priori. The specific statistical tests that will be used for quantitative analysis are selected before the experiment begins. The selection of specific tests is based on the research question to be answered, the level of measurement, the number of groups, and the nature of the data. Run all the tests identified. The researcher must run all tests that were identified a priori, looking at the data and then deciding which test to run can create bias. Although the specific version of a test may be dictated by the nature of the data, for example, using a test for non-normal data, the researcher should not pick and choose tests after reviewing the data. Report all the tests that were run. The researcher must report the results from each test that was run. Selectively reporting or retaining data to support a personal viewpoint is a form of researcher bias that is unethical. Types of quantitative analysis. Quantitative analysis refers to the analysis of numbers. Quantifying the values of variables involves counting and measuring them. These counts and measures result in numbers that can be mathematically manipulated to reveal information. The researcher can think of quantitative analysis as an interpreter that takes raw data and turns it into something understandable. Many types of quantitative analysis are possible. Those available to the researcher can be categorized in several ways: by the goals of the analysis, by the assumptions made about the data, and by the number of variables involved. Goals of the analysis. Quantitative analysis are useful for many research goals. In particular, research questions that focuses on evaluating different groups, for example, between an experimental group and a control group. They are amenable to quantitative analysis. These are also some of the strongest studies when it comes to presenting evidence for practice. Quantitative tests are appropriate to assess the nature and direction of relationships between subjects or variables, including the capacity to predict an outcome given a set of characteristics or events. Researchers also use quantitative methods to sort data. For example, a clinician may identify characteristics that enable him or her to differentiate people at risk from falls from those who are not at risk. Quantitative analysis aids in data reduction by grouping variables into overall classifications, which facilitates determining clusters of symptoms and that may predict complications. Quantitative analysis they're also classified as descriptive or inferential based on the aims of the study. Descriptive studies are concerned with accurately describing the characteristics of a sample or population. Inferential analysis are used to determine if results found in a sample can be applied to a population, a condition for confidently generalizing research as a basis for evidence for nursing practice. Assumptions of the data. Possible, maybe, early on, extra credit points. I have a new cup. I followed my heart, and it led me to coffee. Most of you guys missed the extra point questions, except one person. So you guys didn't watch to the end. Only one person got the extra points in week 6. Good job. Anyway, assumptions of the data. Quantitative analysis are generally grouped into 2 large categories based on assumptions about the data: parametric and non-parametric. These 2 groups of tests have one large differentiating factor: the assumptions about the distribution or shape of the data. Parametric tests are based on the assumption that the data fall into specific distribution, usually the normal bell-shaped distribution. This assumption holds only when interval or ratio level measures are collected or when samples are large enough to achieve normality. In reported healthcare research, parametric tests are the most common, and even when it is questionable whether the basic assumptions have been met, other tests, however, are specific to data that are not normally distributed. If a normal distribution cannot be assumed, then non-parametric tests are needed. The group of tests is distribution-free, meaning the tests do not rely on a specific distribution to generate accurate results. Non-parametric tests are becoming more common, particularly in healthcare, where many variables are not normally distributed. Parametric tests, statistical tests that are appropriate for data that are normally distributed, that is, fall in a bell curve. So it's for data that is normally distributed that fall in a bell curve. Non-parametric tests, statistical tests that make no assumptions about the distribution of the data. Parametric tests are usually desirable because they are sensitive to relatively small differences. They are commonly available in most software packages, and they are readily recognizable by the reader. However, it is not uncommon for them to be applied to data sets where the distribution of the data has not been shown to be normal, and in this case, they may result in misleading conclusions. Small deviations from normality may be accepted with these tests because most parametric tests are described as robust or capable of yielding reliable results even when their underlying assumptions have been violated. Nevertheless, some data are so non-normal as to require a test that makes no such assumptions. Robust tests, statistical tests that are able to yield reliable results even if their underlying assumptions are violated. Compared to parametric tests, non-parametric tests are not as commonly applied, are less likely recognizable, and are not always available in analytic packages. These tests are also relatively insensitive and require large samples to run effectively. When possible, researchers should strive to collect data in a form that can be expected to be normally distributed and to create sample sizes that allow them to use parametric tests. However, researchers should use the appropriate category of test for the data, meaning they should specifically evaluate the results for distribution prior to final test selection. Most parametric tests have a non-parametric counterpart, enabling researchers to apply the correct class of test to the data. Number of variables in the analysis. Quantitative analysis can be classified in terms of numbers of variables that are to be considered. In reality, such tests are classified by both the number and the types of variables involved. Univariate analysis involves a single variable. Univariate analysis are the primary focus of the descriptive and summary statistics. The term is also applied when the study involves a single dependent variable or when only one group is included. For example, differentiating whether blood pressure is affected more by exercise in the morning or the evening is a univariate. Even though two groups, morning and evening, are included in the study, the analysis focuses on a single dependent variable, blood pressure. Univariate analysis, analysis of a single variable in descriptive statistics or a single dependent variable in inferential analysis. Bivariate analysis is the analysis of the relationship between two variables. The most common form of bivariate analysis is correlation. Bivariate analysis is also used to determine if a single variable can predict a specific outcome. For example, determining if blood pressure is associated with sodium intake is a bivariate analysis. In this case, two variables, blood pressure and sodium, are analyzed to determine any relationship between them. Bivariate analysis, analysis of two variables at a time as in correlation studies. Multivariate analysis is simultaneous analysis of multiple variables. This endeavor may address the effects of multiple predictors on a single outcome, the differences between groups on several effects, or the relationships between multiple factors on multiple outcomes. For example, determining if the blood pressure is different in the morning or evening and is associated with sodium intake, weight, and stress level is an example of multivariate analysis. Multivariate analysis, analysis of the effects of an independent variable on two or more dependent variables simultaneously. These analyses become more sophisticated and complex as more variables are added to either side of the equation. On one hand, a research study may require a simple univariate analysis to achieve a descriptive goal. On the other hand, an experiment may require the complexities of a full factorial multivariate analysis of variance, a calculation of the effect of multiple factors on multiple outcomes, taking into account both their main effects and the effects of the interaction of factors. Quantitative analysis can accommodate the complexity of human responses to interventions and illness by reflecting the multivariate nature of health and illness. An overview of quantitative analysis. Inferential analysis is used to determine if a specific result, I'm trying to fix my chair. If a specific result can be expected to occur in a larger population, given that it was observed in a sample. In statistics, a sample, part of the population, is used to obtain results that represent a target population, all of the population. Quantitative research as evidence for practice is useful when it can be generalized to larger groups of patients than those who were directly studied in the experiment. Inferential analysis allows the nurse to recommend that an intervention be used and to do so with the identified level of confidence that it is evidence-based. Inferential analysis. Statistical tests to determine if results found in a sample are representative of a larger population. Inferential analysis is fundamentally an analysis of differences that occur between samples and populations, between groups, or over time because something changed. In experimental research, the change is an intervention. In case control studies, the change is a risk factor. In casual comparative studies, it is a characteristic or an event. Inference is used to determine if an outcome was affected by the change. It is not enough, however, to see a difference between two samples and assume that the difference is the same as would be expected in larger populations. Samples, by their very nature, are different than the populations from which they were drawn. Samples are made up of individuals, and particularly in small samples, we cannot be sure that the sample exactly matches the population's characteristics. These differences, the ones that are due to sampling process, are quantified as standard error. One might view standard error as the differences between samples and populations that are expected simply due to the nature of sampling. Statistical significance. Historically, researchers were interested in finding an objective way to decide if differences between treatment groups and control groups were important. Comparing the differences to standard error made sense. It told the researcher if the change was real. For many decades, researchers have relied on the statistic that is yielded from this comparison. The probability of standard error to determine if changes are different from random errors, that's from Hyatt 2010. This comparison of observed differences to standard error forms the basis for most inferential tests. Standard errors. The error that arises from the sampling procedure, it is directly affected by the variability and indirectly affected by sample size. The certainty with which a researcher can say these effects are not due to standard error is subjected to rules of probability. The calculations produce a p-value or the probability the results were due to standard error. If the p-value is very small, then the probability that the results were due to error is very small, and the researcher can be very confident that the effects of the interventions are real. The largest a p-value can be and still be significant is 0.05 or 5%. If the p-value is very large, greater than 0.05 or 5%, then the probability that the results were due to error is very large, and the researcher cannot draw a conclusion that the intervention had an effect greater than would be expected from random variations. When the p-value is very small, indicating that the probability the results were due to chance is also very small, then the test is said to have statistical significance. It is the comparison of differences to standard error and the calculation of the probability of error that give inferential analysis its strength. However, statistical significance is just one of the important measures that make research applicable to practice. Many readers rely solely on the p-value to determine whether results are useful as evidence for practice. The p-value is often misinterpreted as scientific evidence of an effect, but it is actually a measure of error. Significance testing does not eliminate the need for careful thought and judgment about the relevance of the findings for clinical practice. Inferential analysis yields more than a p-value, and it is these other statistics, the test statistic, confidence intervals, and difference scores, that enables the researcher to quantify whether the difference is important clinical significance. Statistical significance tells us the findings are real. Clinical significance tells us the results are important for practice. This type of analysis forms the basis of some of the strongest scientific evidence for effective nursing practices. Clinical significance. Inspirational thought. It is a perfect day to have a perfect day. It is a perfect day to have a perfect day. Okay, clinical significance. In evidence-based practice, the concern for statistical significance has been augmented with a broader focus on clinical significance. Clinical significance is generally expected to reflect the extent to which an intervention can make a real difference in patient lives. Clinicians are more frequently interested in these findings than in whether the result was due to chance. However, while well-established means are available to assess statistical significance, no single measure can identify clinical significance. Nevertheless, several statistics can inform the clinical evaluation of the importance of a finding, including confidence intervals, minimum important difference, and effect size. Estimates of population values can be expressed as point estimates or interval estimates. A point estimate represents a single number. In other words, a researcher measures a value in a sample, calculates a statistic, and then concludes that the population value must be exactly that number. In reality, samples rarely produce statistics that exactly mimic the population value, called a parameter. In this respect, a point estimate is less accurate than an estimate that includes a range of numbers. The likelihood that a single point represents a population value is quite small. The likelihood that the actual value could be captured in a range of numbers is considerably better. The range of numbers represents a confidence interval and is used to estimate population parameters. Point estimate. A statistic derived from a sample that is used to represent a population parameter. Confidence interval. A range of values that includes, with a specific level of confidence, the actual population parameter. A confidence interval enables the researcher to estimate a specific value. It also provides an idea of the range within which the value occurs by chance. It is defined as a range of values that the researcher believes, with a specific level of confidence, contains the actual population value. Although it sounds counterintuitive, Confidence intervals are more accurate in representing population parameters than are point estimates because of the increased likelihood that an interval will contain the actual value. Confidence intervals are helpful in quantitative analysis in a variety of ways. The calculation of a confidence interval takes into account the effects of standard error, so the probability that the interval actually contains the population value can be determined. Confidence intervals allows the measurement of the effect of sampling error on an outcome and express it in numeric terms. They provide more information than p-values do. They enable the evaluation of magnitude of effect so the nurse can determine whether results are large enough to be of clinical importance. Confidence intervals are constructed using several pieces of information about the data, combined with a decision made by the researcher regarding how much confidence is necessary. Such intervals may be constructed around any statistic, but the mean is most commonly used for this purpose. Confidence intervals for mean estimates and for estimates of the mean differences between groups are popular ways to measure experimental differences, and they represent a critical aspect of application of research as evidence for practice. Their construction requires that the researcher calculate the mean and then determine the range around the mean that is due to standard error. This range is affected by how much confidence the researcher must have, usually 95% or 99%, the amount of variability among subjects, and the size of the sample. At their most fundamental, confidence intervals show the range of possible differences in effect caused by the intervention. They help the nurse determine whether the observed differences suggest true benefits or just minor changes. The confidence interval is particularly helpful in determining how close the treatment came to no difference. For example, a confidence interval for a weight loss strategy might be 0.25 to 2.0, meaning that the strategy could result in a loss as much of 2 pounds or as little as 0.25 pounds. Such an interval is helpful in judging evidence about which treatments might be statistically sound but has little clinical meaningful effect. An additional advantage of the confidence interval is that it is reported on the same relative scale as the outcome itself. In other words, a p-value of 0.02 tells us nothing about how effective a treatment was. Its scale matches that of the probability, ranging from 0 to 1.0. The confidence interval, in contrast, is reported on the original scale of the outcome measure, so it is more meaningful. For example, knowing that the weight lost as a result of the treatment was between 3.5 and 6 pounds gives the nurse valuable information for counseling patients and judging success. A measure of clinical significance that is becoming more and more is the minimum important difference, MID. This clinically derived number represents the smallest difference in scores between the experimental and control groups that would be of interest as evidence for practice. For example, a weight change of 4 ounces may be of no importance in a study of adult males, but it would most certainly be clinically notable in a sample of preterm infants. There are three commonly accepted ways to find the minimum important difference. Compare the change to the outcome to some other measure of chance, anchor-based. Compare the change to a sampling distribution to determine its probability. Consult an expert panel. The MID is determined prior to statistical analysis. The confidence interval is reviewed. If it contains the MID value, then the results are clinically significant. If the confidence interval does not include the MID, however, then the results are not considered clinically significant, whether they are statistically significant or not. To see how the MID is used in practice, suppose a researcher testing the effects of massage therapy on hypertension consults the literature and an expert panel and determines that a change of 5 mm's Hg in blood pressure would be considered clinically significant. If the confidence interval for the change were 1 to 3 mm's Hg, the interval does not include 5 mm Hg, so the result is not clinically significant. If the confidence interval were 2 to 10 mm's Hg, however, then the researcher could draw the conclusion that the findings were clinically significant. Clinical importance can also be represented by effect size, meaning the size of the differences between experimental and control groups. Effect size can provide the nurse with a yardstick to represent how much of an effect can be expected, and therefore it provides more information for evidence-based practice than statistical significance alone. Effect size, the size of the differences between experimental and control groups compared to variability. An indication of the clinical importance of a finding. Effect size is calculated in many different ways, but all have in common a formula that takes into account the size of differences and the effects of variability. Interpreting effect size is relatively easy. Larger numbers represent a stronger effect and smaller numbers represent a weak one. Effect size can also be discerned from a confidence interval. If the confidence interval for a mean difference includes 0 or near 0 on the one end, then it can be concluded that the difference could be nothing. In this case, clinical significance becomes a critical consideration. Both statistical significance and clinical significance are needed to ensure that a change in practice is warranted based on the study results. A change in practice should not be recommended if the researcher cannot demonstrate that the results are real. In other words, that the results are statistically significant. Change also is warranted if the results are not important enough to warrant the effect involved in changing a practice. Effect size is needed to draw this conclusion. No single statistic can be used to establish the usefulness of a study. All of the results taken together provide the nurse with evidence that can be applied confidently. designs that lend themselves to quantitative analysis. Some research questions naturally lend themselves to quantitative analysis. Experimental, quasi-experimental, casual comparative, and case control designs are all particularly well suited to inferential analysis. For example, a research question must lend itself to numerical identification to be appropriate for quantitative testing, and a relationship, difference, or effect must be the focus of the study. Qualitative studies then do not lend themselves to statistical testing because they do not involve analysis of numbers. Predictive and correlation studies also yield statistics, but these do not necessarily focus on differences in groups. A correlation coefficient yields a p-value that represents the probability that the relationship observed is not due to standard error. That relationship, however, may be a weak one, so statistical significance is less important for a correlation study than interpretation of the size and direction of the coefficient. Predictive studies involving regression also yield quantitative output. The regression itself is compared to the mean to determine the value of the prediction. Thus, a p-value in the regression simply indicates that the values are related in a linear way, and that the regression line is a better predictor than the mean. The primary consideration in quantitative analysis, however, is appropriate interpretation. Interpretation should not exceed what the data will support. Appropriately reporting statistical tests and associated effect sizes, along with confidence intervals, is a complete, accurate way to draw conclusions about evidence for nursing practice. All three should be incorporated into the quantitative research report. Selecting the appropriate quantitative test. Conducting an appropriate quantitative analysis depends on the ability of the researcher to select the appropriate statistical test. This is often the most daunting part of the analysis process because many tests are available to the nurse researcher. Each has specific requirements and is appropriate to yield particular information. The researcher must make decisions about the appropriateness of a statistical test based on the following factors: the requirements of the research question, the number of groups to be tested, the level of measurement of the independent and dependent variables, the statistical and mathematical assumptions of the test. Each of these elements is considered in determining which group of tests is selected, and from that group, which particular version will be the best answer for the question without misleading results. Questions about differences between two groups will be answered with different tests than would be used with 3 or 4 groups. Interval data, which are assumed to be normally distributed, are tested differently than nominal data, which must be represented as proportions or rates. All statistical tests have assumptions. The data must meet the assumptions for the results to be interpreted correctly. The tests most commonly used in intervention research are tests of means and proportions. When dependent variables are measured as interval numbers, for example, heart rate, length of stay, and cost, then the mean value can be calculated and compared. When dependent variables are nominal or ordinal, then frequencies, rates, or proportions are tested. In each case, tests may be conducted to determine if differences exist between 2, 3, or more groups. Tests of differences between two group means. Frequently, the research question of interest is whether an intervention, risk factor, or condition made a difference in a specific outcome between two groups. And I do apologize. I have students texting me, so I do apologize having to take a brief break to answer. The typical experiment in which the outcomes for a treatment group are compared to those for a control or comparison group falls into this category. If the outcome can be expressed as a mean, then a Z or T test is appropriate for the use for these differences. These statistical tests indicate whether the differences in mean values between two groups are statistically significant and clinically important. Tests of differences in rates and proportions. Healthcare variables are often expressed as rates or proportions. Events that either do or do not occur, for example, a medication error, characteristics that are either present or absent, for example, risk factor or no risk factor, and variables that describe characteristics in a categorical way, for example, ethnicity or gender, cannot be expressed as intervals. These variables are not expressed as means, so they are inappropriate for tests using the Z or T distribution. 3 kinds of chi-square tests are commonly used in hypothesis testing. tests of differences in means with many groups. Although tests for differences in means and proportions will answer many evidence-based research questions, all of these tests assume that only two groups will be compared. In some cases, more than two groups are involved in an experiment. For example, a researcher may control for the placebo effect by introducing an intervention to one group, withholding the intervention from the control group, and delivering a sham intervention to a third comparison group. In this case, the researcher is interested in comparing the intervention group to each comparison group and then comparing the two controls to each other. Differences between the intervention groups and the non-therapeutic groups will support a treatment effect. Differences between the control and comparison groups support a placebo effect. If the treatment effects are identified without placebo effects, the results of the study represent particularly strong evidence for practice. Tests for non-normal data. Although most data questions can be addressed with statistical tests intended for normally distributed data, some data do not conform to the standard. A moderate violation of the assumptions of a statistical test may still yield accurate results. Many tests depend on normal distributions are robust in this way. However, some data are so skewed as to be inappropriate for tests intended for normally distributed data. If there are no tails in the distribution, then finding statistical significance is a more challenging proposition. Reading the analysis section of the research report. The statistical analysis of a research study provides the tools to determine if interventions do indeed make a difference. Without statistical analysis, a researcher cannot quantify if results are attributable to the experiment or to some random effect. Yet the statistical section of a research article is the one area that is often a mystery. A collection of daunting tables, figures, and numbers that seem to confuse more than they clarify. In turn, clinicians often focus on the methods and then flip the pages to the discussion and conclusion section, taking it on faith that the statistics are reported appropriately. This approach is insufficient to judge the value of a research study as evidence for practice. Studies do get into print with faulty statistical conclusions. Errors, both type 1 and type 2, are made. Authors go beyond what the statistics will support by interpreting output. The nurse must be able to review the statistical section of a research report, both to judge the quality of the article and to decide if the findings should be applied to practice. Descriptive statistics about the sample and variables. Quantifying characteristics of the sample is important for many reasons. Numbers provide information about the size of the sample and the way the adequacy of the sample size was determined. Descriptive and summary statistics familiarize the reader with the characteristics of the subjects, their baseline conditions, and their responses to treatment. The initial part of the results section should provide sufficient descriptive statistics about the sample and each variable so the reader develops a good sense of the characteristics of the sample in the study. This information provides a basis for understanding how these subjects responded to treatment and supports generalization of the study results to other groups. Analysis of sample subgroups. Numbers related to the sample can tell us whether the experimental and control groups are similar enough that extraneous variables are controlled. Deciding whether the results are due to a treatment requires that other potential explanations for a result can be eliminated. Differences in key characteristics of subjects, for example, age, severity of illness, activity level, or ethnicity, may compromise internal validity. Statistics to evaluate the role of error in measures and results. If a researcher could include every member of a population in a study, then sample error would be non-existent. That is rarely possible. However, it is inevitable that there will be some differences between the characteristics of a population and the characteristics of the sample. No matter how carefully the sample is drawn, these differences, which are quantified as standard error, are directly affected by variable and indirectly affected by sample size. As samples get larger, standard error gets smaller. Statistics to evaluate the magnitude of effect. Studies that include inferential tests report several numbers. One of these, the test statistic, enables the reader to judge the magnitude of effect or the size of the differences between groups. Armed with this information, the nurse can conclude whether the difference is large enough to be of practical use. The magnitude of effect helps the nurse make the critical decision of whether to use the results with specific patients. Magnitude of effect can be calculated, but often it is just eyeballed by praising the relative size of the test statistic. Keep in mind that the test statistic is generally a ratio of the effects of treatments to error. As such, this number can provide a rough idea of the importance of many differences that were identified. Numbers that reflect confidence in estimates. When a test statistic is reported, the researcher should report confidence intervals for the results. Confidence intervals indicate the precision with which the researcher has been able to estimate various characteristics or differences between groups. Confidence intervals get larger as they get more precise. They get smaller as they become more accurate. Using quantitative results as evidence for practice. Statistical significance is a requirement for using evidence in practice. If results are due to error, then their application is irrelevant. At the same time, statistical significance tells the nurse little about whether the results will have a real impact in patient care. To make this assessment, the nurse must focus on measures of magnitude of effect and clinical significance. Even with that caveat, inferential results are some of the strongest evidence for practice. Considered the top of the heap. In the most evidence hierarchies, experimental designs provide evidence about the effectiveness of interventions that can be used with a great deal of confidence. When considering the application of inferential results, nurses should evaluate whether the effects make sense in light of the kinds of patients and outcomes that are found in their specific practice. In other words, can the results be generalized to the setting in which the reader is practicing? All of the numbers in the study, taken together, help to answer the question. A systematic appraisal of quantitative information about the sample, the role of error, and the size of effects is required to draw a conclusion about using quantitative research as evidence. Creating quantitative analysis. Creating a quantitative analysis requires selecting the right test, using software correctly, interpreting the output, and reporting the results appropriately and completely. Decision trees in this chapter have provided guidance in choosing the correct test. In general, selection of a test is based on the research question, the level of measurement, the specific statistics used to represent the variables, and the number of groups to be compared. The research question. Specific research questions dictate specific methods of analysis. If words such as relationship or association appear in the research question, then correlation or chi-square statistics should be used. If terms such as differences or cause and effect are inferred by the research question, then inferential tests of group differences are required, such as t-tests, ANOVA, or Mann-Whitney-U. If words such as explanation or prediction appear in the research question, then regression tests should be used. The research question will also drive the choice of variables and the level at which they are measured. The level of measurement. Not all numbers are created the same, and not all numbers in a research study can be treated the same way mathematically. Whether data are nominal, ordinal, interval, or ratio will drive the specific test that can be applied. The statistics used to represent the variables. The selection of a specific test depends on the statistics used to represent the variables. For example, when testing interval level data, means are often used to represent a typical response. Tests of means include several varieties of the t-test or ANOVA. Frequencies, proportions, and rates are tested with chi-square. In addition, the choice of tests should consider the relationship that is expected between the variables. Associations and relationships are tested with different statistics than are the effects of treatments. Sample size will also support or limit the selection a specific test. The number of groups to be compared. When only 2 groups are compared, the role of error is not an issue. When more than 2 groups are compared, however, the error of multiple comparisons should be controlled. This is done by restricting the alpha level considered statistically significant. More commonly, the tests applied are intended to be used as omnibus tests that avoid the multiple comparisons error. It is important, then, that one of the 2 approaches be applied when more than 2 comparisons will be carried out. Availability of statistical software. From a practical standpoint, the final selection of a statistical test is based on access to software that supports the particular analysis chosen. Statistical analysis is much less burdensome when adequate statistical software is used to conduct it. Many packages are available for inferential analysis. Indeed, even Excel will perform most common statistical tests. So there is little motivation for doing manual calculations. The selection of a specific software package depends on many factors, including the user's skill and knowledge, financial resources, and statistical acumen. Some software, such as Analyze It and Stats Direct, are simple to run and inexpensive. These packages support analysis of the most common types of questions. More sophisticated, such as SPSS and SAS, require substantial training and investment to maximize usefulness. Regardless of the complexity of the analysis programs, statistical software is a simple tool. Unless the appropriate decisions and interpretations are made, software will be of little assistance in evaluating data. Summary of key concepts. Inferential analysis is an analytic tool most commonly used in quantitative studies. It enables a researcher to draw conclusions about a population given the results from a sample. Quantitative tests should be selected a priori. All identified tests should be run and reported. Parametric tests are appropriate for normally distributed data. Otherwise, non-parametric tests should be used. Statistical analysis can be univariate, bivariate, or multivariate, dependent on the nature and number of variables involved. Remember the blood pressure, the hypertension, the sodium, that type of thing for multivariate variables. Statistical significance indicates that a result is not due to standard error, therefore the effect can be assumed to be real. Standard error is the amount of variability in the sample that is due to the sampling procedures. It is directly affected by variability and indirectly affected by sample size. Statistical significance should be evaluated in tandem with clinical significance, which determines the usefulness of the results of evidence for practice. Clinical significance can be judged by estimation. Confidence intervals, minimally important difference, and effect size. A confidence interval is a way of reporting results so the precision and accuracy of the estimates can be evaluated as well as size of the effect. Effect size is a better basis for determining clinical importance than for assessing statistical significance. Effect size indicates the relative size of differences that can be expected under similar circumstances. The appropriate statistical test will take into account the requirements of the research question, the number of groups to be tested, and the level of measurement of variables and the assumptions of the statistical test. The Z or T test is appropriate for testing differences between means as a consequence. These tests are useful when differences in the interval level variables are contrasted in two groups. The chi-square is appropriate for testing differences between proportions. As a consequence, it is useful when differences in a nominal or ordinal level variable are contrasted between two groups. The ANOVA is appropriate for testing differences among 3 or more groups, means, and is applied to avoid the error of multiple comparisons. Some data are so normal that they require tests that do not rely on specific distribution. These tests are described as non-parametric, require large samples, and are not as sensitive as other tests. When reading the quantitative analysis section of a report, the NUR should focus on the appropriateness of the statistical selection and key numbers that reflect the role of error and the amount of certainty that exists in the estimates. That concludes Week 7, NUR 410. I am your professor, Marion Johnson. Please email me, text, or call at your convenience. Thank you and have a wonderful week.